Hi everyone, I'm Ahmet and I will tell you more about Prodi, and this will be a hands-on session. So far you had a high-level introduction to what you can do with Prodi, and in this session we will do things hands-on and interactively. I will start with recapping what Tim and Yvette has presented you. So, if you want to analyze a pair of structures, it's usually easy with VMD or Chimera. But when you have hundreds of structures of the same protein or proteins in the same family, it becomes harder, and that's why we developed Prodi. We started developing Prodi 3 years ago to handle hundreds of structures efficiently and to make sense out of those structures. Now, you can build ensembles and analyze ensembles or build A&M models and compare them. And you can also analyze molecular dynamics trajectories using Prodi, and you can compare the tree. You can see how, in this case, these gray dots are from molecular dynamics simulations. The blue and green dots are from analysis of ensembles of structures. So using Prodi, you can see how good you sample the conformations of the protein that you observe in experimental structures. And you can do the same with using E&M models. These gray dots are sampled using E&M models, and you see how it covers the experimental space nicely. Now, these are what you can do, and these are very high level, but Prodi is in the end designed as an application programming interface, or you can think of it as a toolkit. It is designed for performing these, but it's also designed for application development. And that's what I will try to show you now. Okay? And we will use Prodi in an interactive session. We will also use, in addition to Prodi, Matplotlib and NumPy. And this will give you an environment like MATLAB. So before starting, I want to make a quick survey to see whether you used Python or MATLAB or something similar. I'm sure many of you are doing programming. Do you use Python? 2 people use Python. That's great. And do any of you use MATLAB? That's good. More people use MATLAB. And I used to use MATLAB, but when I needed more freedom, I decided to switch completely to Python. And with Python, it's easy. It's more, MATLAB is a bulky package. It's very resource consuming, a lot of resources. Python is lightweight, and it comes with Matplotlib and NumPy. It gives you an environment like MATLAB, and we will see that soon. Okay, so we will get our hands dirty, like Tim said, and I will start introducing Python, some important data structures in Python, lists and dictionaries, and I will introduce NumPy and Matplotlib for efficiency and for plotting, and I will show some essential Prodi features, atom groups. And I start with this because it will be helpful for you to think of atom groups. They are very much like Python objects, like lists, and some of residue, for example, is like a dictionary, and you will see that soon. Now what I will do is I will start an IPython session. Okay, I'm sure most of you are not using Windows, and it will be easier for you to start a command line. Okay, if any of you are using Windows, so what I would like you to do is create a folder like workshop or Prodi. You can name it anything you want, and go into that folder and open a command line in that folder. Okay, so if you cannot open a command line in that folder, just open a command line and try to go into that folder using cd command. So on Windows, when you make a right click, you don't see much, but when you make a shift right click, you will see that open command window here. I will open that command window. I'm trying to make everything visible. Can all of you read what I have in the command line here? If it's not readable, I can make it larger. I will go to a workshop folder, and in this workshop folder, I will start IPython, but I will add this option, --pylab. Now, when you add this option, plotting library and numerical packages will be imported automatically, and you will be entering into an environment which is very much like MATLAB. Okay. Does everyone have access to this environment now? And we will start with simple things. Okay, you can do very basic things, like you can use Python as a calculator. Okay, we will add some numbers, and we can take powers if we want. Okay, more advanced calculations than adding numbers. But we can do similar things with strings too. So how many of you is in IPython now? All right, most of you. That's good. You can do similar things with strings. Okay, so this is a string. Okay, and if you want to, or let's try hello world. Like, I never tried that before. This is a good opportunity to try hello world. So I will have two strings. Now I defined a variable age which holds hello, and then I will define another variable which holds world. Okay, I can use print function to print this into the screen, but now I want to print hello world, and I want to use these two variables. I will use addition to concatenate those strings. Okay, now I have printed hello world. Now, but there is no space between the two characters, and I can add a space. You can make as many concatenations as you want. So this addition operation and others work for strings too. So let's try this now. I want to add hello with a space, and I'm going to multiply this with 10. And what you will see is 10 hellos. Okay? And I will assign this to a variable, age10. Now age10 is when you print age10, when you type in age10 and press enter, it will print a representation of age10 variable. This age10 variable points to the data, and our data is this string. Okay? And now this age10 in Python is an object. It has a lot of methods defined for it. Right? So what I want you to do is type in the variable name that you defined, it may not be age10, and then press period, and then press tab. Okay? When you press tab, you will see lots of handy methods that are defined for this object. And when you call these methods, those methods will operate on that object. Okay? And you can get help for those methods, let's say capitalize. And when you press question mark, this question mark works only in IPython. Okay? It gives you information on the object or on the method. Okay? Now it says that when you call this function, it will return a copy of the string s. String s is in this case age10. It will return a copy of the string with only its first character is capitalized. Okay? Now I call this function like this. You see all age characters are lowercase. Or I can call other function. You want to make this uppercase, you will call upper function. Or you want to make this or you want to count how many hellos there are. Okay, you have a long string and you want to know how many letter H is there. There is 0, because letter H in computers is different from lowercase h is different from uppercase h. Or you can count number of hellos in this. Okay, so it's a brief introduction to primitive types. So numbers and strings are called primitive types, and I will talk about more advanced types now, data structures. Okay, lists, for example. A list is a collection of objects. So these square brackets are used to define a list. Now if I type L, you will see these square brackets, and if I get information on L question mark, it says it is a list, new empty list. Okay. Now I don't want an empty list. I want to put some items in it, and these items can be numbers. I have 4 items in this list. Okay. Now we were talking about summation of strings. We can do summation with lists too. Okay. I have list, and if I add list to itself, I will now have a longer list, and the items in the first list is duplicated. I have numbers 0 to 4, and they are repeated. Okay. Or I can do the multiplication. If I multiply this by 10, it became too long. I will use print here. Okay. Now it printed the list, and you see these 5 numbers are repeated 10 times. And let's say L10. Okay. Oh, I need to remove print. Now I will multiply the list with 10, and I will assign it to the variable L10. Now L10 has some methods too. If you press period and then you press tab, you will see all the methods that are defined for L10. Okay. I can sort this using the sort method, and all the items in this list will be sorted. Now when I print it, I want to print L10, you will see that zeros are at the beginning, and then they are followed by 1s, and then 2s and 3s. Okay. Now this list will be analogous to protein structures. Now when I introduce protein structure data, which is held in an atom group object, you will find that similar things that work for lists also work for atom groups. Now let's say in this L10 list, well, I want to shorter list. I will use L. I want to access an item, and I want to access the first item in the list. Okay. Now what would I do? I would type L1, but it will give me the second character. Okay. As in many programming languages, this may not be true for MATLAB, but for C or Python, or as far as I remember Java, list indices start with 0. Right? Now to get the first item, I need to type in 0. Okay? And then there are a few built-in functions that you might need to use quite a lot. One of them is len function. So when you type in len, it says it's a function, and its name is len. Okay? You can get more information on that. When you call this function with an object, it returns the number of items of a sequence or mapping, or the length of the object. Okay? Let's call len for L. It is 5. We have 5 items in this object. Let's call it for S10. No, S10. H10. H10 has 60 characters, and H10 was 10 times the hello. Okay. Now let's use yes.
Also spaces of characters. No? In this case, also the spaces.
Spaces are characters, right? Each character is 1 byte, when each space is also considered as a character. Okay. Now let's try to do this. Let's access the last item of this list. What would you do? Okay. You would. It is the 4th item, and you would find number. Its index is 4. You would find it using the len function, len -1, 4, and we would put this to use this to index list. Okay. So to calculate the index, we are using len, but we can do this by just omitting this. Okay. L. If I use a negative number, it will give me the item, first item from the end. If I use -2, it will give me the second item from the end. And in addition to indexing, so this is called indexing, you can use slicing too. Okay. I want a larger list now, so I will use another built-in function, range function. Okay. Let's get some information on this function, range. So return a list containing an arithmetic progression of integers. Okay, if I say range rather than reading it, let's use it and learn by using. If I say range, it will return me a list of numbers starting from 0 and ending before 10. Okay, the number that you enter here is not included. Now I can start this range from 5. It will be a shorter range, and I can let's see, start from 0, go to 20, but go to by steps of 2. Now I will have numbers, even numbers, up to 20. Okay. Now let's get a longer range for slicing operations. I have this list. Now I want to get the first 5 items. So this semicolon, right? No, it's a column. Okay. I will use column for spacing. So I want the first 5 items. I will type in here 5, and it will return me the first 5 items. Or let's say I want to access from 1 to 4. I can start from the first item and get items up to index 5. Right? You see, I got this. 4 numbers. Now, okay, I will switch to another IPython features. Okay, if you are using your laptop, you might have it, you might not have it, but it should be available on the classroom desktops. Okay. So I am exiting this session, and in the next session, what we do will be more persistent. We will be able to save whatever we typed in that session, and you will be able to go home and open another computer, and you will remember what you did, and you will keep working on it, and it might be useful. Okay, I will start IPython notebook server, and I will include pylab command, and I will make my figures in line. Okay, so this is what you need to type. This will create a web server, a local web server on your computer, and you will use a web browser to use IPython. Okay. So it may take a few seconds, and you see that a web page. Okay, on my computer, a web page has opened. Do you see a similar web page which says IPy notebook? Okay, great. Now you have it. Inline. So inline means the figures, we will create figures, and they will be shown on that page. If you don't say inline, it will open another window, and we do not want that right now. Okay. Now what we will do is we will create a new notebook. Okay. Just press this, and it will open a new web page. Right, my machine is slow. Could you see the new notebook page? Great. I hope I will see it too. Okay. Yes, I see it too. Now let's try the things that we tried in the IPython black screen session here. Just a few things. Let's try range 10 function. No. Okay. Now after you type in something, when you press enter, it's not going to execute it. Okay. You need to go up here and press this run cell icon. Okay. But to execute things without pressing that, you can type shift enter. When you type shift enter, it will go to the next cell. Okay. If you type control enter, it will execute that cell, and you will remain in that cell. Okay. Whichever works for you, you can press shift enter or control enter, and it will be more convenient than going to this icon and clicking it. Okay. After you printed something here 10, you didn't like 10, you can change it to 1 and then print again. When you are happy with what prints, you can move on with shift enter. Okay. Now after we are done with this session, you can save this. Okay. It will say notebook is saved here on the right hand side. Notebook is saved, and then you can close and halt. Okay, and then if you go home and let me show you what this creates. So in this workshop folder, you will see a untitled IPython notebook file. Okay, if you copy this file to any other computer that has IPython notebook, you will be able to visualize it. You will be able to resume your work wherever you left. Okay, now we will start.
So should we ask if everyone is on the same page?
I think so. Yes, most of you are on the same page, right?
We need everyone.
Oh, well,
We need everyone.
that may not happen. But I will send you my notebook. Even if you don't type in commands now, you can later open this and continue or remember what we did. All right. Now we will start using Prodi a little bit. From Prodi, import start. So this statement means, find the Prodi package that should be installed on your computer, and from that package, import everything. Okay. Instead of, if you put star here, it will be everything. But for now, let's import parse pdb function, and it will going to import only parse pdb. If I type in parse pdb, so there is also tab complementation. Okay, if you write a few characters and press tab, it will complete it. If you press P and press tab, it will show you what options there are. And if you keep typing, you will see parse pdb is one of the options, and you can get information on that by pressing question mark. Okay, so there will be another panel down describing the function or whatever you wanted information for. So this says return an atom group and or dictionary containing header data parsed from pdb file. Okay, now let's parse a pdb file, p38 parse pdb, and to this function it needs an identifier or pdb file name from you. So you can just type in a pdb id 1p38. I will type in 1p38, but you can type your favorite protein. Okay, and when you press enter, it will give you some information. It will, so these information that start with debug or with @ sign and then this caret, you can omit them. It's just making more to make it more interactive. After you parse, if not, nothing is reported, you may not know. It makes you feel better to see something, or for me at least. Okay, so it says that it tells you which pdb file was parsed. So it says pdb file is found in a local mirror, and that local mirror is my computer, and this many atoms and one coordinate set were parsed from that file in a fraction of a second. Now this one coordinate set means it is one model. Okay, if I type another ubiquitin file, it will be 2K39. You will see something different. Okay, I don't have internet. It didn't work. Well, it should work for you. If you're. Oh. What is it? Yes, but I don't want to spend time on setting it up. Okay, so for this one, you should see that 116 coordinate sets are parsed. Okay. Now I will make this smaller, and I will move on to the next cell. Okay. Now we have this P38 object. Okay. If I type in P38 object and variable name, so this is a handle for the data in the memory. The PDB data that we parsed is in the memory, and P38 is just a handle. And when you type that handle variable name and press enter, you see a brief description of it. So it tells you it has this many atoms and nothing else. Well, we can, that's brief information, but when you put more information into this, and you can see more of that. Okay. Now we were talking about lists, right? Let's make a list range 10. And if I want to access the 5th item of this list, I index it. Now I'm going to do the same thing for P38. Okay? If I index P38 using an integer, it's going to give me access to the first atom. Now the first atom is a nitrogen atom in this structure, right? I can assign it to a variable called n, P38 0, 38 0, and now I have access to that nitrogen atom. Okay. Now I want to talk about dictionaries. Okay, dictionaries. I will switch between Prodi and Python. Okay, you will see that Python objects that are very useful for software development, they are analogous. Prodi objects are analogous to these Python objects. And when you try to develop something, you will find that very handy. Okay. Now, by default, every cell that you have is a code, but you can change it to something else. I will change this to header 3, and when I press Shift Enter, I will have a title for this part of this session. Okay. Now we will talk about dictionaries. Dictionaries are mappings. Okay. Python uses the name dictionary to call mappings, or you could call them. Okay. And dictionaries are defined with these curly brackets. Okay. If I type D and question mark, you will see it's an empty dictionary. And I can index a dictionary with strings or numbers. Okay. Let's make this dictionary a dictionary for last names. But when I type in Ahmet, there is nothing in it. Now I will put my last name in that dictionary. Okay. Now when I type D, so you see Ahmet is mapped to Bakan, which is amazing. Now I will map him to Lezon. Now I have 2 items in my dictionary. Okay. What can I do with this? Let's say somebody needed information on the instructors, and if I send this dictionary to them, they will find my last name by just typing in Ahmet. Okay. Now we will go back to atom groups. Okay. Atom groups behave both like lists and then dictionaries. Okay. And you will see when we index an atom group using a key, now this is called a key, and this is the corresponding value. We will do something similar for atom groups. Okay. Chains. Now let's use P38 and let's type in num. When you type in num, you will see all the methods that start with num. If I use num atoms, it will give me number of atoms. P38 num chains. Now I will get number of chains. This has only 1 chain in it. Okay. If I assume that chain is labeled with A, and we will see if it's correct or not. Okay. Now I'm going to index this with capital letter A, which is used by PDB to label protein chains. Okay. And I press Shift Enter. Now I have another object that points me to the data of the protein chain A in this PDB structure. Okay. I will assign this to variable chain A. When I type chain A, you will see this. Now let's use the len function to measure the length of the atom group object. Now if I measure the length of the atom group object, what do you think I will get? Any ideas? Yes, what will be the output? You don't need to tell me. Huh? Number of atoms, yes. So I will get number of atoms. If I do this for chain A, what do you think I will get? No, in this case I will get number of residues. Okay, chain A has, so this is a hierarchical view. Okay, for an atom group, you know, when I started developing Prodi, I spent days to decide what to call the protein structure. Now I could call it structure, but you can use this object for small molecules too. You wouldn't necessarily call small molecule a structure. Now I could call it molecule, but if you look into a PDF file, whatever in the PDF file is not necessarily a molecule. Okay, you have multiple molecules, and those molecules are not complete. So in a strict sense, it's not a molecule. It's just a bunch of atoms. That's why I call it atom group. But still, I implemented the hierarchy that is available in protein structure. Okay. Now what I will do is I will some calculations. I will start another header here. Okay. Now we will do some calculations, and we will, for that we will from Prodi we will import everything. Okay. Now I will type in calc. So in Prodi, functions are categorized. Okay. If you want analysis functions, start with calc. If you type calc and then press tab, you will see what calculation functions are available. Okay. And likewise, if you type show is for plotting functions in Prodi, and you will see what plotting functions are defined. Okay. Now for this protein, let's calculate gyradius. Okay. I will input P38, and from there I will get gyradius, radius of gyration. And I can use this function for chain A2. So is it almost similar? Yes, it's almost identical. Chain A in so I have all of the atoms here. But you know, all the atoms in chain A are not water. So let's try this. I want to see how many water atoms there are in this PDB structure or atom group. Okay, num atoms, and I will give keyword water. Okay, so it says there are 129 water atoms, and the rest should be protein atoms. If I type in protein, I will get number of protein atoms. Okay, now let's say you want to calculate the radius of gyration for only the protein. You don't need the water in that calculation. I will call, so you need to make a selection, right? I'm sure by now you are all familiar with VMD selections, and everything, that selection grammar is available in Prodi 2. You just call select method defined for this P38. If you press period and then tab, you will see all the functions defined. So there are some get functions, and then there are set functions, and we will use among this select function. Okay. Now this will give me a selection of the protein. But you know, you can for interactive sessions, we also implemented this too. You don't need to go all the trouble of writing select. You can just put period and then type in protein, and it will give you the same selection. P38 protein is same as P38 select protein. So if I want to calculate the radius of gyration for just protein atoms, what I will do is I will call the function gyradius for P38 protein atoms. Okay. Now let's go back to chain A. Now when I index chain A with numbers, it will return me residues. This will give me residue 10. Okay. Now for residues, I can do some calculations too. There is calc psi function, for example, chain A 10. It will give me the psi angle, dihedral angle for this residue. Okay. So I could get information on calc psi function. Now this tells me that return psi angle of residue in degrees. This function changed this. Some information that we don't need now. Okay. I have 15 more minutes, and I'm thinking what I should show. Oh yes. So this is about proteins, and then let me show a couple of plotting examples. Okay. Well, Yvette already showed those to you. I will show protein P38. Okay. So it's going to show me a plot of the protein in three-dimensional space. This is in line, we won't be able to rotate. But this function also could take chain A as an input. Okay. It's showing. Okay. Okay. This is enough for ProD, I think. If you go to tutorials page, oops, I don't have internet. You will see very detailed tutorials. Okay, one of them is ProD tutorial. This will show you the basics. It will give you an introduction to most of the things here, and then you can, this is about. If you don't want to type in code, you can do normal mode wizard to make some calculations also. You will learn it from here. And then these will give you some more detailed information. Now here in this interactive session, I want to introduce arrays to you a little bit, and matplotlib functions, okay? Arrays and plotting. And I'll make this a heading. Now, we have a list here, range 10, okay? Oops. Now, lists are Python objects. Python is an interpreted language. Now, using an interpreted language has advantages. When you want to get something done, something computational, and you need to write a program, by using Python, you can write your code faster than you would, than writing the same code in C, for example. In C, you would have to go into the trouble of compiling it and building it. With Python, most of your calculation needs, you can do it in interactive sessions, and you see every command that we typed in was interpreted, and we got some output. But this also has disadvantages. This might be slow at times. When you want to read millions of atoms from a PDF file, and if you use Python objects to handle those atoms, it will be very ineffective, and I will try to demonstrate that. Okay. Now in Python, in ProD, the ProD features are Python objects. You are using the Python interface, but in the background, ProD is using NumPy, and everything that you parse from PDF files are stored in numerical NumPy arrays. The operations that we perform on those are performed in the background using C, optimized C code. So that's why, despite using Python for structural analysis, you feel that it's quite fast. Right? Now we have this list, and we can convert it to an array using array function. Okay, this array function comes from NumPy. Now it pretty much shows the same thing, but you have this array surrounding the list that you have. Okay, so I will show that this is much faster than a list. Now there is this timeIt function. Okay, it's a percentage sign and then timeIt and print 5. It is going to print 5, and it is going to time the. This is taking too long. If it's taking too long, if you did something you didn't want to do, you should usually be able to stop this, but now it became unstoppable. So, to time something, wait. Oh, all right, yes, it's done. This was a mistake. When you when you're trying to time something, you shouldn't print it to. It shouldn't print anything. You see, it has performed 100,000 operations, and in each loop, it performed this action 3 times, and it shows that it's, to time it really, it's repeating the action too many times, and it's taking the best time to calculate the actual CPU time that it took. So to print 5, it took only 17.2 microseconds. Okay. Now we are going to do this. Okay. Let's create a list. L is range. Now I will create a big list. Okay, a long list with let's say 100,000 items, okay? Length of L is 100,000. Now I want to convert this to an array, okay? Array, and the input will be list. Length of array is also 100,000. Now I can use sum function. This is a built-in function to get the sum of all the items in the list. Okay? So if I sum these numbers up, there is an analytical solution to this, but for demonstration purposes, we won't use it. Okay, sum of numbers up to 100,000 is this. Okay, now let's time this, how long it takes to sum this up. It was oh yeah, I said time, right. This should be different. Oops. Okay, it took 23 microseconds per loop. Now we will repeat this with NumPy array. Instead of using the built-in sum function, I will use the array function, a. Now a is an array. If I type period and press tab, you see all the functions defined for that array. So I can call sum function. It will give me the sum. For arrays, I have max function. It will give me the maximum number. Now I will time this. I will call sum function. So 23 millisecond versus 23 millisecond versus 125 microsecond. It was almost 200 times faster. You see, now you want to solve a problem. Like I said, you might have option to use C or NumPy, or Python. Using C will take longer time to develop, debug, and compile things like that. Python, you can get development faster, but it will be slower. But if you start using and becoming familiar with arrays, you can make things much faster. Before I developed Prodi uses arrays to hold data and to parse data. There were some other Python PDB parsers. They would take up to 10 seconds to parse a single PDB file. Now using NumPy, that came down to a fraction of a second. And now Python really became suitable for analyzing PDB structures in interactive sessions. Now let's...
Are you talking about the constraint
BioPython and MMTK parsers. Yeah, two of them. I had used two of them. BioPython has a parser, and it's purely Python as far as I know. And then MMTK from Konrad Hinsen from France. He has another parser. That's, I guess, even slower. Now let's do some plotting. Okay, we are in a PyLab session, and we have all the plotting functions that that is available. Okay, we will plot numbers from 0 to 10. Okay, this will show us a plot of this, a straight line. Okay, now since all NumPy features and Matplotlib features are available in this session, we can create some random numbers. Okay, random. If I say 10, it didn't work. I didn't call the right thing. I guess random. Okay, so in this case, random is a module, and you cannot really call modules. And you see the functions in this module. Random, a description of the function that we used here, uniformly distribute values of a given shape. Now the shape that we give is let's give another shape. So this 10 means give me an array of 10 numbers. If we give 3 by 3, it will give us a matrix of 3 by 3 with fill in with random numbers. Okay, and then there should be a function called normal. Normal, is it there? Let's see. Yes. So this normal function creates random numbers from Gaussian normal distribution. Okay, and let's say random numbers. I want 1000 random numbers, and I want the mean. Oh yeah. So you see the arguments here. Location is the mean of the distribution, the center of the distribution. So I want the center of this distribution to be at 10, and then I want to scale this distribution standard deviation by 2, and I want 1000 numbers. Okay. Oops. I shouldn't have written this. Okay, now I have 1000 random numbers. Okay, to see if they are really drawn from Gaussian normal distribution, we will use histogram function. Okay, so this histogram function is a matplotlib function. If you give a bunch of numbers, it will create a histogram for you and plot it, and the input will be random numbers. Okay, and you have a Gaussian plot here. Now, so far you have seen how Prodi objects are similar to Python objects like lists and dictionaries, and then you have seen how using NumPy you can be much more efficient than you would be with using pure Python, and we have seen some plotting functions. Okay. I was going to show you more about. Yes. What is it? Well, it's almost 12, and at 12 we have a question and answer session. Now, shall we do some question and answers? And if okay, now what I will do is I will just save this and halt this, and I will go back to an example that I prepared before coming here. Yes.
So there is a, I guess, documentation somewhere about the.
Yes, yes, there is.
So can you do computations like RMSG?
Oh yes, of course. Yeah, I will show some of that now. Okay, in this example, and I hope to finish in 20 minutes. And if you have any questions, I can take it. Okay, I'm closing this now. Okay, shut down. Now this is another example. Okay, I will go here and rename this example. Is it gonna open?
You said you will send us these?
Yes, I will send these notebooks to you. Well, not send them, but we will make them available on the website, and you will be able to download from here. Okay. I will rename this. You can also rename your session too. Now this is taking too long to load because I have output also. You can go here and clear all the output to make it more compact. Okay, all the output will go, and this will be easier to handle. Now I will call this hands-on session. Okay, I'll save it. I will close and halt it. Now I will go back to P38 ensemble analysis example. Okay. Now I prepared this before, and this is available in Prodi tutorials in more detail. Okay. Here I will just quickly go over it. Okay. Now in this example we are analyzing 76 structures of P38 MAP kinase. Okay. And we will analyze a predefined list of PDB structures. So here I created a, okay, let's start from here, execute this code. Everything from Prodi is imported. And now I am here, I will execute this too. Okay. And now I have a list of PDB identifiers. Now let's check the size of this P38 PDBs list. There are 75 structures. Now we are going to analyze these 75 structures. We will build an ensemble. Okay. Now, to build an ensemble for multiple structures, of course, you need a template structure, right? You will pick one of those structures from the ensemble, and you will take the rest, and you will superpose all of those structures to the reference structure that you picked. Now, here I picked 1p38. 1p38 is an unbound structure of p38 MAP kinase, and it is one of the most complete structures of p38 MAP kinase. So if you have 20 structures, the best structure to choose would be the most complete. Many X-ray structures are missing residues here and there. A loop might be missing, a terminal might be missing. So the best choice is the most complete one. Okay. Now we have parsed p38, and here for efficiency we parsed only subset of atoms. C alpha. So it says only 351 atoms are parsed. Waters and non-alpha carbon atoms are omitted. Okay. Now from here I want to select subset of residues. Okay. These subset of residues are present in almost 90% of these structural ensemble. Okay. And from here I end up with a chain. Okay, you can get more description of these functions and methods later, but in this reference structure part I want to end up with a reference chain that I will use for building my ensemble. Now before going to ensemble building part, I will show how we compare two chains using PRODI. Okay. Now we will read another p38 structure and we will call it other. And we will, I'm going to parse a random structure, I don't know, structure 50 from this, let's say. It could be anything. Okay. And it is parsed and it has this many atoms. Now let's show, using this show protein function, let's show these two structures. Okay. So you see, blue is p38, the first one, reference structure that we parsed, and the cyan is the other structure that we parsed. Now we want to superpose these two structures. Now first we need to do a mapping. Okay, we are going to map the other structure onto the reference chain that we have. Okay, after this mapping, you see some debugging information here, or useful information. It says it is comparing chain A from this structure with chain A from the reference structure, and after this comparison it mapped 221 residues, and it will give you the sequence identity between these mapping. Okay, so probably there were some mutations in the other structure that we parsed, and the overlap is 98%, which means that some atoms in this other structure were missing. Okay, well, it's not important. If a structure is has missing atoms, PRODI is more forgiving than VMD, and you can still do superposing and RMSD calculation. So from this mapping, I have an atom map object. Okay, two atom map objects actually, and I am accessing them with indexing, but I will make it more clear. P38, other mapped atoms, mapping 0, 0.
So what kind of object is mapping? It's like a double array mapping?
Mapping is a list.
Is it this?
Yes. So you are comparing two structures. Each structure may have multiple chains, and after that comparison, if there are multiple matches and multiple mappings, you will have a list of mappings. Usually the first mapping in this list is the best mapping, but based on the thresholds that you give, sequence identity threshold, you might have multiple mappings, and they will be sorted based on the sequence identity.
Okay, and right now we have two it's a list of double list, like you have 0, 0, 1, 1, or like what's this structure?
Okay, let's look into it a little bit. Okay, let's look at type of mapping. Mapping is a list. And let's look at length of mapping. It has length 1. So it has only one mapping. So both structures had one change, and we ended up with one mapping, right? And if I access the first mapping, so in the indices start with 0, if I access the first mapping has 4 items, okay? And if I look at the type of the first mapping, it's a tuple or tuple. So it's another object, but it is similar to lists, but it has some essential differences. You can extend a list, you can add items to list, but tuple, you cannot change it. It is immutable, okay? So, depending on what you want to store, if you want to say store something that doesn't change, you can use a tuple, okay? So, best mapping, let's get this, best mapping 0, and I have the best mapping here, best mapping. Okay, now I got rid of this list and I have the first and best mapping. If I look at the first item, it is the other structure. So it is chain A atoms that are mapped to reference structure atoms. Okay. If I look at one, now it is chain A of the reference structure mapped or matched with the other structure atoms. If I get the third item, it will be the sequence identity that is reported to you here, 99% sequence identity. If I get the third item, it is the overlap which is reported here. Okay. Now I will get these from the best mapping, and I will use them to calculate RMSD, other reference. So the RMSD between these two is 51.2 angstrom. You see they are far apart. Okay. Now we will use superpose function. Okay. And I will just use the variables that I defined for them. And I execute this. It's going to superpose the two, and it's going to return me the minimum RMSD between these two structures. And now if I want to show these two structures again, you will see that they are nicely superposed. So this is useful representation. It's not the best you get, but for an interactive session it helps to see how a superposition is done, for example. Now we will build an ensemble. The things will get a little bit more complicated. In this structure comparing chains part, we compared pair of chains, and in ensemble, PDB ensemble, or let me call this building PDB. In this part, we will repeat this comparison 75 times for each pair of structures. Okay. Now we start an ensemble object. Now ensemble object is an object that stores coordinates, but this is a PDB ensemble object. It's a specialized form of ensemble. It can store coordinates with missing atoms. So you are analyzing tens of structures, and each of them has missing atoms here and there. But if you remove all of those missing atoms from your ensemble, you will lose too much information. Now, to be able to extract something useful from that, you need to preserve the structures with missing atoms, and to hold that coordinate data, you use the PDB ensemble object. Now, I had defined reference structure above. Now I will use it to initiate the ensemble. Okay, I will use the reference to set the atoms of the ensemble, and I will use the reference coordinates to set the coordinates of the ensemble. Okay, after this, the ensemble has changed. Now it has 0 conformations. Conformation means a PDB structure that we put into this. Okay, and it has 321 atoms. 321 atoms, if you go above, is the number of atoms in the reference chain. Okay. Now we are going to build this ensemble. You see, we are going to iterate over.
Sorry, why did you define Q38 graph?
I define it here. I don't have internet, but if you you can find these range of numbers on the internet in ensemble analysis tutorial. So you can copy and paste from there. If you go to this tutorial, and then there is heterogeneous ensembles or heterogeneous data sets example, you will be able to find those numbers in there. Okay. Now let's go back to tutorial building part. So I didn't show you making for loops, and I'm going to show you shortly here. Okay, let's create a list range 10. And let's make a for loop. For I in L. Print I. Now what does this do? So we have a list here. Print L. We have a list here, and I made a for loop. And I use this form. Okay, for I is a variable in L. It means that for every item I in list L, for every item, take the items in list L and assign them one by one to I. So for every item in this list, the item is assigned to I, and then here you can do something you like with I. You can take the square of it, or you can print I and it's square. Okay. Now we are going to do something similar with list of PDBs. Actually, let's repeat it here. For PDB in PDB list. Print PDB. Okay. So you see the PDB identifiers is printed one by one. Okay. Now here we are going to get PDB identifiers one by one, and we are going to parse PDBs one by one, and for efficiency we are going to parse only C alpha atoms. Okay, and after parsing a PDB we are going to use map onto chain function, and we are going to map that PDB onto the reference chain that we identified above, and then from that we are going to get the first best mapping, and we are going to get the first item from that mapping, and that item is going to be the atoms that we want to put in the ensemble. And then ensemble has a add coordinate set function. We are going to pass it to here, add coordinate set map. It's going to automatically get the coordinates from this object, and this object might have it might have atoms missing. Okay, I can go back to chain comparison here. Oops. Other mapped atoms get flags. So this has flags defined for. You can use this function to get flags defined for each atom. Okay, I'll execute this, and you see a list of booleans, false and trues. All of these are true. So it means that all of the atoms of the other structure are mapped onto P38 kinase. But if there were missing atoms, some of these values would be false. Okay, and we are using these flags to let the ensemble know which atoms are false, which atoms are there, and which atoms are missing. And we are going to label this conformation using the title of the PDB. Okay, I'll just execute this, and we will analyze this ensemble sum. Okay. Now you see lots of output. It prints an output for every PDB file that is parsed, and you will see that the results for comparison of every pair of structures. Okay. So the analysis is complete, and here we timed this analysis. Okay, we how many seconds it took, we calculate that. So if you look at timing, 75 structures were analyzed in 13 seconds, which is not bad in an interactive session. You don't have time to get coffee for yourself. It's that fast. And then for every second, for every structure, we spent 0.2 seconds to read the structure and map it onto the reference structure. Now let's look at this ensemble. Ensemble has 75 conformations and this many atoms. Okay, we can use calc occupancy function for this ensemble. Okay, so what does calc occupancy do? It returns occupancy calculated from weights of PDB ensemble. So, you know, occupancy means the fraction of fractional presence of atoms in the ensemble. I'll pass this ensemble, okay, object. So you see some of the atoms, you know, we had, you see number 75 is the maximum. So it means that this residue was present in all of the structures and this residue was missing in one of the structures. And then there is also this show. For many calc something functions, there is also show that thing function. Okay, now I used calc occupancy and now I will use show occupancies and I will pass the same object. And you will see the occupancy plotted based on atom index. Atom index is in this case residue index. So you see which parts of the protein are missing in most of the structures. So if I go back to the beginning, so when I'm building this reference, I selected only part of the residues. So I knew this protein before, that's why I selected them. So when you do a similar analysis for your favorite protein, first you can start with analyzing all of the atoms of that ensemble. And then you can plot occupancy and see which residues are missing most. Okay, and then you can build the ensemble for a refined data set. Okay, but there is also this, or you can do this. There is trim PDB ensemble function. Okay, trimming means it's removing the things that you do not want from in the ensemble. So you can build the ensemble for all atoms, and then you can use trim PDB ensemble function. It will return you a new PDB ensemble obtained by trimming given PDB ensemble. Okay, and this function helps selecting atoms in a PDB ensemble based on one of the following criteria and returns. So you can trim an ensemble based on occupancy. If you say take this ensemble and trim it for 80% occupancy, it will give you a new ensemble in which all atoms are present in at least 80% of conformations. Okay, but we didn't use it, and probably I don't use in the examples, but so that you are aware of it. Now I will interpose the ensemble. Interpose, what it does is, you know, you calculated with a reference structure and you mapped all other conformations onto that reference structure. You can superpose them, but if you prefer to do interpose, it will do this. It will do a superposition and it will calculate the reference coordinates by averaging all other conformations, and then it will continue doing this until the average conformation doesn't change. And by doing this iterative superposition, you remove all the translations and rotations from your ensemble, and your ensemble will become ready for PCA calculations. Now I will go over these very quickly. This is how you do PCA calculations. You create a new object, you build a covariance matrix using ensemble object, and you just calculate the modes. Okay, doesn't take too long. So we analyzed 75 structures within seconds, and now I will do A&M calculations for my reference chain. Okay, A&M is also done. Now I will show overlap. Okay, now this shows you the agreement between experimental data and theoretical predictions for how this protein moves. Right, and you see the so maybe I can spend some more time on PCA object. Okay. Now we calculated the PCA object. What is it like, right? So if I I already typed in PCA object, and you see what it contains. It contains 20 modes and 321 atoms. Now if I index PCA object, I will get mode 1 from this object. Now this mode 1 is the most dominant mode in this ensemble. If I calculate its fractional variance, okay, PCA 0, this first mode explains 30% of the structural change that you observe in this ensemble. Okay, I can repeat this for I in range 10, print PCA, let's print mode, and then let's print calc fractional variance of that mode, PCA I. Okay. Or we can do this to be more efficient. Mode is PCA I. Now in Python, you always try to be efficient, because if you don't, it may take forever for some calculations to do things. Now here I am doing the same action twice, okay, and I try to avoid doing it twice. This is the indexing operation, and even an indexing operation to access an item in a list or container, it takes nanoseconds or microseconds depending on the object. Now instead of doing it twice, I am doing it once here, and I will use mode variable to do that. If I press execute this, you will see the first mode, first PCA mode, explains 30%. The next explains 17%, then 10%, and then most of the variability is explained by first 6 modes or so. We can also plot fraction. Plot. No, not plot. Prodi is show fractional variances. If I give this object to it, so you will see that fractional contributions are plotted for this PCA object. First one is almost 30%, decreases, and if you take 10 modes, it means you are almost describe all of the changes in the ensemble. Okay. Now here we compared A&M and PCA modes quickly, and we can make squared fluctuations, but we are going to normalize them. Since these are two different data sets, if we don't normalize them, you will see, let's try without normalization, and then we will do normalization. So, A&M modes are compressed. The force constant, and by changing the force constant, you can make these curves comparable. But instead of that, you can normalize both curves, and you will have a plot that is comparable. Okay. Now, what you can do is you can write an NMD file, P38 PCA NMD PCA object P38 reference. Okay, let's do this. Let's get some information on this. So this function returns file name that contains modes and atoms data in NMD format. And NMD format is the format that normal mode wizard reads. Okay, and the input for that is first argument is file name, the second argument is modes that you want to put in the file, and the last argument is the atoms, so that you have atomic information in. So I will write this, but this is going to write 20 modes now. Instead of writing 20 modes, probably I will want to analyze top 6 modes. I can make a slice of the PCA object, and I will end up writing just 6 modes. Okay. Now let's, I didn't show you, but maybe here I can. I can show you writing a file or reading a file. You can open a file for reading this built-in open command. Okay, we will read this file now and print the things in it onto the screen. Okay, input, or I will call it NMD file. Now it says that it's an open file here, and what we will do is we will read lines one by one. For line in NMD, this is something you might need, and I just wanted to show you. We will read lines one by one, and we will print those lines onto the screen to see what an NMD file looks like. And I don't want to print all of the lines. I will just print 20 characters from each line, and I execute this. Okay, 20 is too few. I'll go to 60. But I need to open the file again. Okay. Now when you reach the end of the file, if you repeat the reading process again, it won't read anything because you are at the end of the file. And here what an NMD file looks like. It contains atom names, residue numbers. It contains coordinates of the reference structure, beta factors for the reference structure. It contains modes. When you use a normal mode wizard to visualize motions, these modes, these numbers are what are used for making those arrows or animations. Okay, I'll save this and I will stop here. If you have any questions, I can answer. If you don't, you'll do more of these.
It's not a fixed width.
It's not. It's space separated.
Okay, because that coordinate line has been super
Yeah.
long, right?
Yeah.
X, Y, Z for you.
This is XYZ. This is the X of first atom, Y of first atom, and you know, it's not. It's separated by space. That's how NMD reads. Okay, so I mean, my suggestion is this: you use IPython notebook to do the examples. I don't have internet here, but if you go to Prodi website, you will see that copying and pasting examples is fairly easy. So you will see a code example here. If you click here, you won't see this input number anymore, and it will be easy to copy that code and paste anywhere you want. Or let's say you have a long example and you want to take that code and execute in Python, you can just press show code here, and it will collect all the executable code from that page, and you can select that code and copy into a file. Okay. So there are a few tutorials for the afternoon. The Prodi tutorial is an introductory tutorial. You see the important features of Prodi, and you see some ensemble analysis, some ENM analysis, and some structure analysis. And if you, let's say, want to do ENM analysis, you can pick this one. If you want to analyze ensembles, there are 4 different examples here. One of them is taking a sequence input and searching the PDB for that sequence, and then downloads all the structures and analyze them for you. And in structure analysis, there are some examples which shows you how to identify contacts between ligands and proteins. And there is an example, for example, which takes an ensemble of structures and identifies any ligands in that structure and extracts all the ligands. If you are interested in protein-ligand interactions, you can look into that. If you want to analyze trajectories, you can look into this. So Prodi might be preferable to VMD in some cases. VMD loads all of the trajectory into the memory. Now in these computers, you have only 4 gigabytes of memory. If you have 30 gigabytes of a trajectory file, it won't fit in the memory, and you want to calculate some angle in that. You can use Prodi for that purpose, for example. And then there is conformational sampling example. It uses ANM modes to generate alternate conformations of the protein, and then it uses NMD to minimize these conformations. And in that example, NMD is used for minimization purposes only, but it also uses multi-processing standard libraries of Python. So you generate 40 core conformations, and 40 conformations are processed simultaneously on your computer. So if you have 4 CPUs, it will show you how to execute 4 NAMD instances at the same time. And this also might be useful for docking purposes, conformation. So in protein ligand docking, you usually want to incorporate protein flexibility, and this shows a quick way of generating alternate conformations for docking.
So once you have
NM mode, you have the C alpha carbon
Yes.
structure, right?
Yes.
Is truly reversing and going back to all atom?
It can. So there is
And
a
that's which is optimized by NAMD, the all atom?
all atom is optimized by NAMD. So you create an C alpha model and then you extend it to all atoms. So the other atoms of the same residue moves in the same way C alpha carbon does, and you generate ensembles, conformations for that extended model, and NAMD optimizes that. So it's a simple function that does the job. That example. Okay, this is end of my session. Thanks for your attention. So I was saying that you can start a notebook, copy and paste what you want to do, and save it, and then if you want, work on it later, anywhere. Right? I will make these examples available, and maybe I will point to some other useful introductory Python tutorials.